So what I'm going to do is I'm going to tell you about recent work in my group. The members are over here of postdocs and graduate students. And I'm going to tell you about an adjacent field, if you like, cavity optomechanics, which is a platform we have explored over the last year or two on nonreciprocity and synchronization, two things which have come up here over the last couple of days as well. So I'm going to put that into perspective. Before I plunge into that, I just want to mention that in my group, there's a bit broader effort on looking at various platforms for quantum science and technology. So at the core of what we're doing is we're looking at how to create, control, and exploit quantum coherence, and that from a few body to a many body perspective. So systems we've been looking at are called atoms, are mechanical systems, nanowires, circuits, diamonds, quantum dots, and also magnetic systems. I'm going to focus here on the mechanical systems. Before doing that, I just want to mention that there was ongoing work in my group before over the last year on cold atoms and also on spin chains. So with that, I'm going to show you what I'm actually going to talk about. So I'm going to give a short introduction on cavity optomechanics. Some of you are really very familiar with that. Some might be almost orthogonal to that field, so I feel it warrants a short introduction, at least to have on a common page. Then I will show you two examples connected to that field of recent work of ours. So one is to engineer structures which are actually breaking the reciprocity, the Lorentz reciprocity of the Maxwell equation. So you have some elements which are do have not statistics. When I exchange input and output, they don't have the same transmission. So that's non-reciprocal devices. And then, time permitting, I will show you a little bit about synchronization, how I think about it, motivated from these mechanical systems. So here's the structure we are thinking about in cavity optomechanics in the field of optomechanics. So there's mechanical degrees of freedom and there's cavity degrees of freedom. And so one picture you can have in mind is here is a Fabry-Perot cavity. There's a moving boundary condition here at the end. So you can focus on one cavity mode described by a bosonic operator A. And you can think about the center of mass motion of this mirror at the end described by the variable x. In the simplest of all situations, we can focus actually on 2 degrees of freedom. One is the mechanical motion of this object here, which we call phonons. Note this in contrast to condensed matter. This object here doesn't have any dispersion. It's really a localized mode. It's a center of mass degree of freedom of this mirror here. It's operating at a frequency omega m. And then we have the single mode degree of freedom of this cavity field described by a bosonic operator A. And now crucially, this cavity frequency depends on this parametrically on the displacement x. So these are the photons I'm going to talk about. And so for small displacements, you can expand this dependence here of the cavity frequency on the displacement x in a Taylor series. And for most situations, we can focus on this linear term here. So there's a linear, the position of this displacement modulates the cavity frequency. And if I put that together, the interaction Hamiltonian between the 2 harmonic degrees of freedom, A and B, is given by A dagger A, B plus B dagger. So that's one way to look at it. It's a modulation of the cavity frequency. That's one way to look at the Hamiltonian. You can turn it around and look at the other way. And you can write it as a force onto x. So this is the force operator. And then the force operator can be identified as A dagger A, obviously. So that's the photon number. And that's the physics of radiation pressure. So this is a radiation pressure force, the number of cavity photons inside the cavity pushing the mirror. And indeed, that has been explored in the last decade or so. That's the Hamiltonian. But actually, we're not only concerned with the Hamiltonian structure, but this is an open-driven quantum systems. So we have to not only think about the coherence, but there's also dissipation. So the system is actually usually operated far from equilibrium, where we have laser driving from the outside, we have photon decay from the cavity, and we also have a thermal bath basically given by the substrate of this mechanical degree of freedom. So a much more appropriate picture to look at is actually this one here. So you have, here's the Hamiltonian coupling cavity and mechanical degree of freedom, but both of these are coupled to bath. One is at finite temperature, and one is usually assumed to be at 0 temperature. So then you take that together with the non-linearity of the radiation pressure interaction, and that gives you very rich physics, even on a classical level. So there's steady states, limit cycles, and even classical chaos. This is realized in a large variety of different systems, one of which has made a huge number of waves in the last couple of years, obviously. And that's where actually a lot of the questions have originated from a long time ago. I'm much more interested in these more microscopic implementations of this idea. So some of which are in the optical domain over here. This is a photonic crystal. This is a whispering gallery mode. Some are in the microwave domain, such as this one here. This is a superconducting circuit structure. And they go down to levitated objects over here, and even ultra-cold atoms in cavities. So they span a huge different range of frequencies and mass scales. But in the end, they actually implement, they're dominated by the same type of Hamiltonian I showed you in the beginning. So this is, again, the interaction Hamiltonian. This is the radiation pressure coupling, A dagger A plus times X. And now let us start looking at that in a formal way. So here, this is this interaction Hamiltonian. But in a lot of structures, this is actually a relatively weak force. So what people do is they pump the cavity field strongly so that it makes sense to think about the cavity field as a coherent state plus fluctuations. So you separate out coherent part and fluctuations. And then you rewrite your Hamiltonian. The most important bit is this one here. So this is the fluctuations coupled to the mechanical degree of freedom. And let me put this into a picture. Here's my cavity, and now I'm driving strongly with my laser beam. And now this coupling here, what it tells you is that at the expense of one drive photon, you can create a photon in the cavity at a slightly different frequency if you want. And that, at the same time, destroy or create a phonon. And that's how in this structure you can couple gigahertz to, or down to kilohertz to terahertz. So you're starting from a parametric interaction, which is up here, under strong driving that linearizes and becomes a resonant interaction between the fluctuations and the mechanical degree of freedom. So you have a picture where you're looking at, which looks like this here, where you have the fluctuations of the cavity, which are coupled to the mechanical degree of freedom as such. And so this interaction is now, you see this alpha here, this is the mean field. It strongly enhances the cavity, this coupling. So now you have something which can actually be dominant. And this is the dominant force in these structures. It can be enhanced, it's reconfigurable, and it comes also with a tunable phase, which will become important later, which is given by the drive phase. So there's actually a whole toolbox you can now do, depending on where the driving is relative to the cavity resonance. Your laser is relative to the cavity resonance. You can be on resonant, below or above on the two sidebands, as we say. So they're given by, the tuning is given by the mechanical frequency. You can choose your Hamiltonian, in a sense. So you're turning this general Hamiltonian to something where you resonate enhance one process over the other. And that will become useful in a second. So for a while, people were mostly interested in this one here, which is the beam splitter type interaction, the cooling interaction. So by that, you're converting a phonon to a photon, and it's quickly dissipated, and thereby you can actually cool the mechanical motion. And for a while, of course, that was a big goal, and it's really a starting point for this whole field. So up to like 2011 or so, there was a lot of a race to the ground state. So here is just showing several experiments, and the message is here just several systems have reached this ground state. We have mechanical motion in the quantum regime at the level of B dagger B on the order of 1. So there's a macroscopic, mesoscopic degree of freedom, which is close to its quantum ground state. And that has been really a starting point where now people have put on top of that more quantum control, so more refined ways of this quantum toolbox to start to see strong coupling effects, even exploring coupling to multiple modes, etc. And where we stand now is that we have the different experiments I showed you are targeting quite different types of physics. Some of the levitated ones are targeting quite fundamental questions, so thinking about fundamental tabletop science, I would say. So they're thinking about decoherence and about thermodynamics, creating macroscopic superposition states and such. It's going to be quite hard, I think. But then there's other degrees of freedom, such as the photonic crystal structures, which are tailored to do dissipative many-body systems. So you can engineer several of these mechanical structures which are coupled to each other, and then you can start exploring topological phases under drive, and also this, what I talked about, quantum synchronization. Others are interested in, and then this, the focus of this conference comes into play into thinking about coupling to other hybrid devices, so such as cavity fields to other collective degrees of freedom, such as the macroscopic spin of a ferromagnet. And finally, we also start to explore ways to have an impact on quantum technology with these amplifiers and transducers and non-reciprocal devices. So especially the last bit has been now supported by a European network, which I'm very excited about, which is called HOT, so Hybrid Optomechanical Technologies, which are in the objectives have exactly these goals: to build a transducer which is quantum limited, to build a non-reciprocal device, as well as exploring the more many-body physics of the mechanical motion coupled to optical fields. Locally, that means there's a collaboration between Hitachi and myself, and it's all led by EPFL as a leading house. So with that, I would like to come back to the outline and now explore these two directions we've been followed up over the last couple of years. Why would we be interested in having a non-reciprocal device? It's actually a very common situation in the lab that we have a source, a quantum source, or a classical source, or a signal source, which we're interested in measuring and exploring. And on the other end, these signals are usually pretty weak, and we have to amplify them, and we have a readout chain on the other end. So quite naturally, we want to have that the signal from this side here reaches our amplifier chain, but the amplifier noise and the noise of the readout chain does not penetrate through to the quantum source. So for that reason, we need a non-reciprocal device in the middle, such as an isolator or a circulator, which does that job. One structure where that's particularly interesting, I think, is in the quantum domain. So in the regime or in this domain of circuit QED. And currently, what is used there is the magneto-optical effect. So going back to using small pieces of YIG, which actually breaks the Lorentz reciprocity of the Maxwell equation. And then you can have this is a circulator or an isolator. But there's actually a whole field, and it's not limited to optomechanics at all. So there's actually quite a few structures where people are trying to replace these macroscopic isolators and circulators by an on-chip reconfigurable alternative. And that's, here are two recent reviews about that. If you look about the simplest case, maybe the simplest non-reciprocal device is an isolator. You can think about these devices really on a device level, so you can ignore all details. For what you as a user care about is really a black box description. So here is your black box, or my black box here, my black box isolator. And it's a two-port device, 2 ports in, 2 ports out, as indicated here. And the desired scattering matrix I've indicated here. It's a linear device. It's described fully by its scattering matrix as given here. So you want that everything which goes in here goes through, say, and on the other side, the reverse, you want to have this completely absorbed and not end up in the signal here. So if you look at the scattering matrix, then formally you could say non-reciprocity is linked to the S matrix being not symmetric, so that this expression holds. There's some recent work on this problem, especially what we've been especially motivated by. But let me focus on our approach here. So now let me just tell you how we start to engineer coming from the mechanical interaction to a non-reciprocal device. And what we use is slightly more complicated. So we are using 2 cavity modes, 2 mechanical modes, and we therefore have 4 lower sidebands. And we're driving close to all of these 4 lower sidebands. So there's 4 drives, they're close to all of these sidebands. So that's why you have a beam split interaction, or what I said cooling before, of this type between the mechanical degree of freedom and the optical fluctuations. And you end up with, you have then, in that case, you have engineered in what we call an optomechanical plaquette. So you have coupled the 4 degrees of freedom in your game, the 2 cavity modes and the 2 mechanical modes, in such a ring-like structure to each other. And all these couplings here are of the type of this driving enhanced optomechanical coupling. They all come with a phase, and the important bit here is that there's only one gauge invariant phase of these, basically the sum of the drive phases. And that plays the role of an artificial magnetic field for the phonons and photons in, if you want to be fancy, in a synthetic dimension given by these drives. So explicitly, you have broken time reversal symmetry in the problem. The Hamiltonian of this structure is really a very simple one. It's the one where you have a single particle, non-interacting, and it hops around this ring under the influence of a magnetic field which is threading this ring. So it's very simple. Let's think about what the input-output structure of that is. So that's just the Hamiltonian again. Now we're including the dissipation channels. So now let's take away this additional link again, and we're thinking just about 3. So we have here the cavity modes and coupled only by the mechanical degree of freedom. Then we are in the structure of having a transducer. We're having something which does frequency conversion between, between these 2 frequencies over here. This is reciprocal. So if I look at the S matrix, S21 and S12, the frequency dependence is just the same. Now I switch on this link. Now I close this loop. And now I can, crucially, now I can have interference between different pathways. So now I have interference between going from here to here via the upper path and the lower path. So indeed, this formula, which is given here, shows you the level of the strength of the amount of non-reciprocity. If this is 1, it is reciprocal, or modulus 1 is reciprocal. If it's away from 1, it starts to be non-reciprocal. And here in the formula, you have exactly these coupling elements. So you have from here to here a response function going here over here. And now you add amplitudes, and then you square. If you go the other way, you have to go through that link in a different way. So you pick up the opposite phase. So there's the influence of the artificial magnetic field in here. And that we have 2 paths. We're actually using interference of 2 pathways. If everything's just the same, there will be interference, but interference will be the same backwards and forwards. But now, if I start to break, so I slightly detune these in the middle from each other, then I open up a small window of non-reciprocity because I have over here I have the S matrix going from 2 to 1. There's constructive interference in that direction between the 2 processes, and I have destructive interference in the other. So close to this, here I have the situation where I do have transmission in the one direction and no transmission in the other. How is this done actually in the lab? So this has been done in the lab of Tobias Kippenberg at EPFL. They are implementing things on the microwave domain. So this is lumped element, as Jake briefly alluded to. This is lumped elements. So this is a capacitor. It's a capacitor plate, very vacuum gap. And this now you have a drum mode, which moves up and down. If this displacement now modulates the capacitance of the LC circuit, that changes the resonance frequency of the LC circuit, and you're back to the same Hamiltonian what I talked to you in the beginning. So it's a microwave circuit optomechanics implementation given by the same Hamiltonian. This is detailed, so we're using 2 cavity modes, coupled to 2 mechanical resonances of the same structure. So actually, physically, there's only one of these capacitance, and this is actually the result. So the message here is really it works. of these, the sum of the drive phases, you can engineer both a reciprocal situation as well as non-reciprocal in one direction, non-reciprocal in the other. And you can completely fill in this this pump phase dependence, and you see nicely it matches the theory. This is the ratio which I showed you before, and this is the level of non-reciprocity in the circuit. So this is really at the level of 20 dB, a reconfigurable on-chip electromechanical circuit. So it leverages the mechanical motion to achieve non-reciprocal behavior for these microwaves. It features low insertion loss and also low edit noise, which is important for the quantum domain. I should also mention that everything I said so far is on the level of coherent signals. You don't see any whether this is quantum or not. You can also study the transduction of noise which is coming in the circuit, and it's also non-reciprocal, but that's a different story. All right, so actually there was quite some progress over the last year on this domain. 3 groups, oops, I think this is almost dying. 3 groups have looked into similar types of structures over the last year. What we wondered now, we've been looking at how to change this, how to make this different structure, and we have exchanged these red drives here in a theoretical study by looking at various possibilities and trying to point out future possibilities for these circuits. Just want to highlight 2 things. So if you replace 2 of these red drives by blue drives, you're realizing a directional phase-preserving amplifier. So it has the same level of complexity. It's as hard as the other one, and it's featured by this scattering matrix on resonance. It features unlimited gain and can be quantum limited. And the second option is to drive with 6 drives in this fashion here. Then you have a phase-sensitive amplifier which features unlimited gain and unlimited gain bandwidth product. Again, quantum limited, or can be quantum limited in strong coupling. So let me just wrap up that bit and just point out to you that we also looked into taking this principle of thinking about using an effective magnetic field or together with interference. We've also looked recently at whether that can be done in the fermionic setting. So looking at a quantum dot, where we looked at whether we can build basically a diode out of interference. It has also shown up the same physics in sideband asymmetry. I won't go into detail of that. And finally, everything I reported so far is Gaussian, and we very recently looked into the non-Gaussian bit. So we're using 2 different drives on the level of reservoir engineering here to stabilize underdriving non-classical massive states in these oscillators. But with that, I'd like to come back to the outline and use the remaining time of a little bit more than 5 minutes or so to think about quantum synchronization. So synchronization goes back to this gentleman over here who wrote in a letter to the Royal Society. Back in the days, you don't wrote to Nature, but you wrote to the Royal Society of London. So he wrote and he reported that he had observed an adjustment of rhythms of oscillating objects due to weak interactions, nowadays called synchronization. So nowadays we know it's everywhere around us. So it's in fireflies' heart, in the brain, in animals, populations. In physics, it's all around us. In this field, particularly in the form of spin-torque oscillators, but also in Josephson junction and lasers. And finally, in the classical domain, you have power networks showing very similar behavior. These networks' behavior is very interesting. So it's really ubiquitous around us. So what is actually synchronization is actually a little bit more subtle. When you look into textbooks coming from the nonlinear dynamics literature, what you find is the basic starting point is always a self-oscillator. You're starting, or also called limit cycle oscillator. You have something basic like a metronome. So it is powered by an external energy source, and it has a natural frequency which it runs at. Just notice this is not a simple harmonic degree of freedom. So it's really, you need some sort of nonlinearity which limits the growth of the amplitude in these type of objects. And then if you have two of those, or several, or a whole collection, then you can think about coupling the two, and then these two different metronomes running at different speeds can change their frequency, and you can draw the following diagram. You can plot the difference in frequency after coupling as a function of coupling. And then if you're close enough, the coupling is strong enough to overcome the difference, then they lock, and you can talk about synchronization plateau. So that's a very typical setting of these self-oscillators and synchronization. A slightly simpler situation is if you're doing ejection locking. So then you replace one by an external degree of freedom, which is not changed. It's kind of master-slave kind of setting. So what has this to do with optomechanics? So with optomechanics, you can have actually explore a similar situation as been pointed out by explored by Flo and Markert first in his group. So thinking about mechanical degrees of freedom and these optical degrees of freedom, you can actually drive on the upper side band, and then you're pumping the system. You're not cooling, but you're pumping the system with energy. And if you overcome the internal dissipation, the system starts to self-oscillate. So a single one of those can now self-oscillate. It goes into a limit cycle. And if you do that, then you can, of course, start to couple them, say, by this bar over here. And then you can talk about synchronization physics of several degrees of freedom. And if there are in the quantum regime, you can ask the question whether quantum fluctuations have anything to do about it. Have any influence on this. So in the interest of time, I will just only flash just the basic idea. What we've been looking at, actually, this limit cycle oscillators of an optomechanical system are very rich. They show multi-stable behavior, dynamic multi-stable behavior. So what we looked at most over the last couple of years is the driven van der Pol oscillator, a much simpler setting, which has the basic ingredients for these limit cycle oscillators. It features a nonlinear damping in the form over here, and a linear anti-damping, as well as an injection locking driving. So I'll be quite quick here. You can rewrite things in an amplitude equation. You can go into radial motion and phase. You get these type of equations here, and they are quite nice because they give you a lot of the physics. So you can see that this is the anti-damping curve as a function of radius. There's your limit cycle, which is stabilized at a certain radius. And this equation over here is quite central. It's called Adler equation. So it's the physics of an underdamped particle in the tilted washboard potential. So you can think about the tilt and about the depth of this potential. And you can be in two situations. Either this tilt is large and the valleys are not so deep. Then the particle just rolls down the hill. And that translates into where your phase just winds up and you're unsynchronized. Or you can be the opposite situation. Valleys are deep and the particle is trapped. This is the synchronized state. So this is a setting of synchronization in this van der Pol type self-oscillators. What we've been then exploring is, this classical equation of motion. What we then start writing down is a quantum van der Pol oscillator. This is a Lindblad type equation which features the same type of terms. So it has a detuning, a drive, a nonlinear damping, and a negative anti-damping over here. So in that sense, in the correspondence limit, this one goes back to the classical equation of motion. And then we started to look at that, and we found that the normal classical locking behavior is perturbed by the influence of quantum fluctuations. So that's great, but actually we wanted to have more. We wanted to see something more genuine quantum mechanical in this problem. And we saw that as soon as we added some nonlinearity to the problem, so nonlinear in the term of a Kerr Hamiltonian to this degree of freedom, which makes the harmonic ladder unharmonic. And then we saw actually genuine quantum features in the sense that if you were to simulate this problem completely semi-classically, in terms of, say, a Fokker-Planck equation, you would obtain a very broad locking behavior. So this nonlinearity just makes the locking very broad. If you're simulating the system quantum mechanically in terms of the master equation, you find these resonances over here. And so here are the Wigner plots connected to these resonances. You can also understand them perturbatively from analytically. And in that way, you can trace them back to the underlying unharmonic level structure, that these resonances here are really coming from the energy quantization of your oscillator in the, below your self oscillator. So in that sense, these multiple phase locking resonances are footprints of the quantized energy levels underlying your Hamiltonian. Yes, and with that, I'm at the end. This is my conclusion slide. What I showed you is that cavity optomechanics, a close variant of cavity optomechanics, is a different platform for looking at new quantum science and technology. I alluded to two directions we've been looking at over the last couple of years. One is non-reciprocal devices by using these reservoir engineering techniques of using interference and magnetic fields. And they're also fun to explore things like synchronization and the impact of quantum fluctuations on this. Thank you very much.